Hey everybody, let's get things going. That's not what I want. One moment. There's the attendance form. I should pin my video, obviously. There we go. Wow, my hair is looking extra special today. Not that you guys care, it's all right. What are we doing today? Today is the Whitener Day. Hello, good to see you guys. I just want to remind everybody that I have an office hour this afternoon from, I believe, sorry, my brain's always a little tired after 16B. I have an office hour today from, holy smokes, 2:30 to 3:30. I believe that is the right time. And let me also, here is the, what is going to be, can I type that in there? That doesn't, well, that's, I was trying to copy the invitation so I could give it to you guys, but it seems like it doesn't want me to, so I got it here. Here is the Zoom meeting information. You can also find it in Canvas if you're looking for it. So there are the usual things. I wish I could space this out a little bit more. Here is the attendance link one more time. Okay. And again, today is the day we focus on Whitener's class. Thursday is the day we focus on Nundara's class. Not that we can't address each other's classes on the opposite days if we have to. So what do you guys want to talk about? What kind of questions you got? I've been getting pretty caught up on the OLI stuff, so I think I can address most of the questions you might have. But what do you want to see? Outcomes are not equally likely. Maybe. Let me think here for a second. So I've got pencil over the floor here. An experiment where the outcomes are not equally likely. Why is this harder to think of than it should be? Let me see here. I think I had some stuff written down. Yes. So, well, let's do some Googling. So I will admit, this is kind of the hard part about stats. Sometimes it is coming up with examples. I'm sure I've said that before. But let's Google around and see if we can find experiments where the outcomes equally likely. Let's see here. Yeah, and that's exactly the example I was going to think. It was like, well, if you have a coin that's not fair, that's definitely an example that people often use. So, for example, you can certainly say, let's say we have a pretend unfair coin where the probability that this pen is trash. I'm going forward to you can say like the probability of getting ahead is 5/6. 5, I went 3/4 actually. Or 4/5. And the probability of getting a tails is 1/5. This is that would definitely be an example of an experiment where the outcomes were not equally likely. Another example of that would be, and this actually, so this feels like a less realistic example, But a realistic example is an unfair die or a weighted die. And there are definitely examples of people cheating with unfair dice in games of chance. You could have dice that are weighted so that, and so I'm going to make, so typically you would have a dice weighted, so you could have like a 7 roll, so typically you'd have like a 6 and a 1 weighted on either die. This is a little bit complicated. Let's pretend we have 1 die, so that a 6 rolls, let's make the numbers easy. 7/12 of the time. And everything else, 1, 2, 3, 4, and 5, each roll 1/12 of the time. That would be another example of an experiment where you have sorry, I forgot the words, where you have outcomes that are not equally likely, right? The rolling of the die is the experiment, and the outcomes, rolling a 1, 2, 3, 4, 5, or 6, are not all equally likely. There's a much higher chance of getting a 6. But again, I think it's not. I feel like they're kind of contrived a little bit. But there are lots of different things that you could say. The number of phone calls you get in an hour, right? The different possible values for that are probably not all equally likely. But if you're talking about more physical things like rolling dice, flipping coins, the usual assumption is that all the outcomes are equally likely unless you have some other piece of information. We can definitely talk about Bayes. So it's actually Bayes' rule. There's no R on it, but yes, we can definitely talk about Bayes' rule. In fact, yeah, you guys have a whole list of things that you guys did send me. So let me first talk about the complement rule, which is certainly useful. So the complement rule is that, well, there's a couple things. So there's a number of ways of stating it. So we can look at the Venn diagram. So this is your whole sample space, and you've got some thing A there. Then everything outside of A is the complement of A. So a few ways you can kind of phrase the complement rule are the following. You can say that A union A complement should be the entire sample space. You can also say that the probability of A plus the probability of A complement should be the probability of being in the entire sample space, which is just 1, because the entire probability should have to 1. So if either you had A happen or you had A not happen, those are kind of the only 2 possibilities when we're talking about one particular event and its complement. And usually the way this ends up getting phrased or expressed is that the probability of A complement is equal to 1 minus the probability of A. That is usually the way people think about it. So let's actually do an example with this because, let's see, I had it. Okay, yeah. So let's say we're taking a multiple choice test that has, let's not make it too terrible. Let's say it has 10 questions. Each question has 3 possible answers, only one of which is right. So 3 possible answers, A, B, or C, only one of which is right. If you're just guessing, right, the probability of getting any particular question right is going to be 1/3. So let's say, so what I'm working towards here is a binomial thing, which also kind of addresses the complement thing. So the probability of success, success is obviously getting the question right? We'd love to be able to guess all the questions right if possible. So let's say P, probability of success is 1/3. And then, of course, the probability of failure, which sometimes people call Q, 1 minus P is 2/3. And so, hello. Let me put the attendance one more time just so you guys have it. There's the attendance again. So we can ask all sorts of questions, like what's the probability of guessing all the questions right? What's the probability of guessing all of them correctly? Well, that's going to be 1/3 times 1/3 times 1/3, 10 times. I'm going to write it that way first. So one way you can write it is 1/3 to the 10th power, which is going to be 1/3 to the 10th, which is something. But there's actually more to it than just this. So I'm going to go back. So the probability really is, well, let's say X is the number of successes, the number of questions we get right. And I'm trying to find the probability that X is equal to 10 for this binomial random variable. And so the way we're going to calculate that is it's going to be, well, I want 10 successes. So I want out of 10, I'm choosing 10 successes. Or if you prefer, you might also write this as 10C10. Right, there probably is a button on your calculator if you have a calculator. I don't remember if I think this was in office hours on Thursday. I was looking for the button on my calculator and it was really easy to find. I'm going to show you guys up close. So if you can see this right here, it's this button right here. Hopefully you guys can kind of see that. It says NCR and NPR and it says a little exclamation point on it. So if you wanted to, you could type 10 and then hit NCR and then also 10 again. It would give you 1 because there's only one way of choosing 10 things out of 10 things. You choose all 10 of them. Just like there's only one way of choosing 0 things out of all 10 things. You choose none of them. There's only one way to do that. And then we would multiply by probability of success to the 10th power, because we want 10 successes, times the probability of failure to the 0th power, because if there's 10 successes, there's exactly 0 failures. And that's going to be exactly 1 times 1/3 to the 10th times 2/3 to the 0th, which just ends up being 1/3 to the 10th. Okay, so now I'd like to ask a more interesting question. And this is where we're going to use the complement rule to make our life suck less. So I want to find what's the probability that we have greater than or equal to 3 successes. So what's the probability that I guess 3 or more of the questions correctly? And so this would be terrible to calculate. Because if you're going to do this the long way, say, well, it's the probability of 3 successes plus the probability of 4 successes plus the probability of 5 successes, all the way to the probability of 10 successes. I'm getting a phone call from Placerville. That can't be important. Sorry. This is awful. I don't want to do this. So instead, right, I mean, we could calculate this. This would be 10 choose 3 times 1/3 to the 3rd times 2/3 to the 7th, plus, then we do it for 4, 10 choose 4 times 1/3 to the 4th times 2/3 to the 6th, plus all the way to the last one. That's kind of a lot of calculating. I mean, there are calculators that will actually do all this for you, but I'm not imagining that's the intention that at least Whitener is having for you guys. So the way you would actually calculate something like this, relatively straightforwardly, is you would use a complement. You would say, oh, the probability that X is greater than or equal to 3 is equal to 1 minus the probability that X is less than 3. Right? We're either bigger than or equal to 3 or we're less than 3, and that kind of takes up everything. So this probability plus this probability is equal to all of the probability, which is 100% for 1. Now, here's the thing. If I got less than 3 questions right, it doesn't mean I got 2.9 questions right, or 2.8 questions right, or 2.75, right? I got 2 or 1 or 0. You can't have a fraction of a question correct. So really, when you're talking about a discrete random variable, where the possible outcomes are just nice integer values typically, this is equal to 1 minus the probability that x is less than or equal to 2. Because being less than 3 is the same as being less than or equal to 2 if your only options are integers. All right, so I suppose I could have looked at page 119 also, because maybe they say something else. I'll look at that in a second. So the way you would do this here, say, well, that's not so terrible. The probability that x is less than or equal to 2, there's only 3 things I have to worry about there. It's the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. So at least in this context, the point of using this kind of complement rule is to make our calculation less terrible. Let's see, so we end up getting, so the probability that x is equal to 0, well, there's 10 choose 0 times 0 successes times 10 failures. And that's the probability of getting 0 questions right. There's one way of getting 0 questions right. You got all of them wrong. Times 1/3 of the 0 times 2/3 of the 10. Plus the probability of getting 1 question right. 10 choose 1. There's 10 different ways you can get 1 question right. You get the first one right, the second right, the third, the fourth, the fifth, etc. And then times 1/3 to the first, times 2/3 to the 10th. Sorry, to the 9th, right? We got 1 success and 9 failures. Plus, and then we'd have 2 successes. 10 choose 2. So there's 10 choose 2, which is 45, because 10 times 9, really, right? It's, if you really care, it's 10 factorial over 10 minus 2, which is 8 factorial times 2 factorial. 10 factorial over 8 factorial, the 8, 7, 6, 5, 4, 3, 2, 1 cancel, and you just get 10 times 9 over the 2 factorial, which is 2 times 1. That's 90 over 2, which is 45. Choose 2 is always pretty easy. It's just the number of times the next smallest number divided by 2. And then it's going to be 1/3 to the second times 2/3 to the 8th. And so here's what this looks like. So I think I can fit this in. So 1 minus 2/3 of the, 1 minus all of, this is a little bit smushed in here. 2/3 to the 10th, that's this first part. This is 10 times 1/3 times 2/3 to the 9th. So that's going to be 2 to the 9th over 3 to the 10th. Plus 10 choose 2, which we just said was 45. 1/3 squared times 2/3 to the 8th. You're still going to get a 3 to the 10th on the bottom, right? All of these will have a 3 to the 10th on the bottom, and then you'll have a 2 to the 8th. So calculating that will take a hot minute here. Let's see what we've got. So, okay. Blah, sorry. So 2 divided by 3. This is terrible. This is what, so, sure. 2 divided by 3 to the 10th. Plus, so I'm going to think of this as 10/3 times 2/3 to the 9th. That seems a little bit easier. So 2 divided by 3. Sorry, this takes a minute. Also, my room is getting really hot, I gotta say, which is unfortunate. I wish my TI-83 still worked, but it died, which is unfortunate because I really like that calculator. So we've got, let's see, 10/3 times 2/3 to the 9th. And then finally, here I'm going to have 45 over 9, which is just 5, times 2/3 to the 8th. So I've got plus 5 times 2/3 to the 8th. Hopefully this isn't too terrible. I made a mistake, of course. Well, darn it anyway. Okay, how do I get out of the syntax error? Sorry, I've broken my calculator. Oh, I see. Okay, that's easy to fix. Okay, hopefully I fixed it. I did. So we got 0.299. So our answer is 1 minus that. So we get 1 minus 0.299, which is 0.701. So it looks like there's about a 70% chance of getting at least 3 of the questions right. Okay. Let me just look real quick at the page that was referenced just to see if there's anything else I'm missing about this. I don't think so, but it's always good to check. Yeah. Yeah, so yeah, I think we've pretty much covered it. Basically, if you know the probability that an event happens, you also know the probability of its complement happening, which is just 1 minus that probability. So let's go ahead and go over Bayes' rule, which is always interesting. And let me make up some numbers here. And I'm going to give it to you kind of the standard context, I feel like. I mean, there's multiple contexts, but the one that always seems the most logical to me is about basically testing for, so you can talk about drug testing, you can talk about testing for disease. I think there's one there about testing like to see if someone's a spy. I like the disease testing because it seems reasonable. So here's the typical kind of setup. The probability, so let's call D for having the disease, whatever it is. There's lots of examples that use AIDS, and plus for testing positive. Also, a lot of these examples go with the tree diagrams we'll also talk about here. And so the kind of typical setup is the probability of having the disease, we can say AIDS if we want, is super low. Let's say it's like 0.00003. Probably smaller than actually. I don't actually know. Sure. And then, so again, this is just if you randomly select someone in the population, the probability that they have this disease is 0.00003. Or if you do decimal over 2 places, it's 0.003%. So 3/1000ths of 1%. And then the probability of testing positive, given that you have the disease, should be high, right? You want your test to be accurate. So if someone has the disease, the probability that they test positive, given that they have the disease, should be something like 0.98. And then I think we also need to give the false positive result. Yeah, the probability that you test positive, given that you don't have the disease, should be something fairly low, but you don't want to have a lot of false positives, so something like 0.05. And if you don't have the disease, and so this, sorry, by the way, this notation is D superscript C. That superscript C means the complement. So D is having the disease, D complement is not having the disease. So a couple other things we can discern from this right away. If we know the probability of having the disease is 0.00003, then the probability of not having the disease, the complement, is 1 minus the probability of having the disease, which is 1 minus 0.00003, which is 0.99997. All right, and that's all we have right now. So a couple questions we can ask about this. Yeah. So the first kind of question I want to ask is, if you randomly select someone, what's the probability that they test positive? And then the more important question, the question that's going to get at Bayes' theorem, is what's the probability that they have the disease given that they test positive? And the thing that we're going to point out here, that we're going to notice, is that this conditional probability of having the disease given to test positive is going to actually be very different than this conditional probability of testing positive given that you have the disease. The words kind of make them sound like they might be the same, but they're really not. Testing positive given that you have the disease should be very high. Having the disease given that you test positive might not actually be. Yeah. All right. So, but let's look at this one first. And I guess we have enough room. So this actually goes to, well, I want to do this. So we're going to make a tree. And I forget how they phrased it in the OLA course. I know I read it. Basically, the first branch of your tree should be the thing that kind of doesn't depend on the other thing. So if I'm thinking about, having a disease or testing positive, definitely testing positive depends on having a disease and not the other way around, right? Having a disease is I don't want to say independent, but it definitely makes more sense to branch it off as having the disease or not having the disease. And writing the little probabilities in there. So the probability of having the disease, is 0.00003, I think I said, right? Yeah. And the probability of not having the disease is 0.99997. Okay, and then from each of those, two different things can happen. So at this point here, now my branch is always looking stupid for some reason. At this point here, two different things can happen. You can either test positive or you can test negative. Same deal here. Right? If you don't have the disease, you can still either test positive or test negative. And each of those have a probability as well. So if you have the disease, the probability of testing positive, given that you have the disease, we said was 0.98. Which means that the probability of testing negative, given that you have the disease, is the complement. It's going to be 0.02, right? One of those two things has to happen, and their probability has to add to 100%. So the nice thing about these tree diagrams is that each branch should add up to 100% or 1. Similarly down here, we know that if I don't have the disease, the probability of testing positive is 0.05, or we call it false positive. So we know that this branch here has a probability of 0.05, and that means this branch here has a probability of 0.95. It has a 95% chance that if you don't have the disease, you will test negative. Okay, so the first question was, what's just the probability of testing positive? Well, to find that probability, I'm going to find all the paths that get me to being positive. That means I'm going to look at ending up here and ending up here, right? Those are the places where I've tested positive. So that's going to be this path, which is going to be this times this, because, well, in fact, I'm going to write it out. So I'm going to write it out in two different ways. It's the probability of having the disease and testing positive, plus the probability of not having the disease and testing positive. We could draw this graphically. Sure. So here's my Venn diagram of the entire population. Here's I'm going to make it kind of small. Here's the small segment of the population that have the disease. Here's the small segment of the population that don't have, or the large segment that don't have the disease. And then in this little circle here, let's see, disease positive. My circle back and look very representative, right? But here's the people that test positive. So here's the people that have the disease and test positive. Here's the people that don't have the disease and test positive, which is exactly right. So here is this, people that have the disease and test positive. Here's this, people that don't have the disease and test positive. And those together give you all of the people that test positive. So this is, I think, what's called the rule of total probability. Usually they skip over this, or we may not skip over this, but they get to the fact that we can write this as the probability of this, probability of D and having the disease and testing positive, is the probability that you have the disease times the probability that you test positive given that you have the disease. And then, right, because you're saying, I have this, and then I have this, but this is conditioned on that we already did this, so it's a conditional probability. Plus, the same kind of deal here, the probability that you don't have the disease times the probability that you test positive given that you don't have the disease. You don't have to write this out if you can draw the tree, right? We can just draw the tree and be like, okay, well, how can I test positive? It's going to be having the disease times the probability that I test positive given that I have the disease. So of the 3,000th of the percent of people that have the disease, 98% of them will test positive, and you get those two multiplied together to figure out what percent of those people test positive have the disease, plus same kind of calculation here, 0.99997 times 0.05. So calculating that. So here's what we can see. This is going to contribute most of it, right? Because you have almost 1 times 0.05. So let's see. We have 0.00003 times 0.98, which is 0.0000294, plus 0.99997 times 0.05, which gives me a total of 0.0500279, which is pretty close to 5%, right? It's a little higher than 5% of the population. But most of that is taken up by all these false positives, right? There's a lot, right? Since there's such a large population, these people are making up the majority of the positive tests because there's just, even though the test is pretty accurate, there's just so many people in the population that 5% of them testing positive kind of is the bigger piece of the total positive tests. But now we want to ask the more interesting question, and let me erase this over here. And this is where Bayes' formula or Bayes' rules come into play. What's the probability? Let me use a different color pen. What's the probability of having the disease given that you test positive? And this is where, so I usually think of this Bayes formula as a two-step formula, really. Whenever I see a conditional probability formula like this, I always jump to thinking, oh, that's the probability of the intersection of the two things divided by the probability of the given thing. Maybe I shouldn't have erased that picture. That picture was kind of nice. Yeah. But then we need to go further because, well, so we actually just figured out the bottom part. So here's the way this ends up working. The bottom part's always the total probability. In fact, so we could even, yeah, I'm going to do one intermediate step here. So this is the probability written like this of having the disease and testing positive, plus the probability of having the disease, or sorry, not having the disease and testing positive. And then we've got this on top, having the disease and testing positive. So the nice thing to recognize, I think, here is that this thing you're calculating here is going to show up right down there as well. So here's how this ends up looking. It's, well, we know how to calculate the probability of having the disease and testing positive. It's the probability of having the disease times the probability of testing positive given that you have the disease. So it's P of D times P of testing positive given D divided by, all my pens are dying. It's time to break out some new pens, I guess. The same thing shows up again. Plus this thing over here, which is the probability of not having the disease times the probability of testing positive given that you don't have the disease. So that's what the formula looks like. So if I'm trying to find the probability of some conditional probability, but actually in the other direction, you end up writing it as, okay, well, it's all of this. Now, I probably have never actually memorized this formula. I probably worked it out every time I used it just because it helps me think about what I'm doing. So even though it's, I mean, I don't know. I don't think you should memorize this formula. I think it's kind of weird to memorize it, but we certainly could. So here's what I'm calculating. I feel like I shouldn't erase this because it's useful. I guess I'll erase my tree. Kind of like my tree though. No, fine, I'll just erase this. Here's what I really got. So if I'm finding the probability of D having the disease given that I tested positive, so it's going to be probably having the disease, 0.00003 times the probability of testing positive given that I have the disease, which is 0.98, divided by that same thing right there. Now we already calculated this bottom part, right? That's what we just did before. It's the 0.0029 whatever number, plus the other one, which was the 0.9997 times the 0.05. Okay, let's see what we get when we calculate this. So, okay, sorry. So this number down here, I'll remind you, is 0.0500279, which I know I erased. So I'm doing as I'm doing this, 0.00003 times 0.98, which is going to be about 0.00003, divided by this bottom part. And I'm getting 0.00058 approximately. I'm going to round that. 0.00059, let's say. So really small, right? The probability of having the disease, given that you tested positive, is, you know, not 1%, not 0.1%, but 0.05 or almost 0.06%. So really, really low. And the reason is because even though the test is accurate, there's so many false positives just because of how large the population is. So the probability of having the disease given you test positive is really, really low because most of the positive tests are false positives. So that's what's happening in this particular example. And that's an example of Bayes' formula. So let me write out the formula more generally. Again, I would encourage you, so when I think about Bayes' formula, I mostly think about writing out a tree diagram, because usually that's going to help me. So if I'm trying to find something like, you know, if I know the probability of A given B, and I want to find the reverse conditional probability, probably of B given A, I'm going to say, well, here's Bayes' formula. I mean, I think of it in two steps. First, the conditional probability is the probability of the intersection divided by the given probability, and right, the second one is the given thing. And then I'm going to rewrite the top using the known conditional probability. So it's the probability of A. I feel like I always want to write it backwards. It's the probability of B times the probability of A given B. If you want to know the probability of B and A, well, first B has to happen, and then A given B has to happen. And then divided by the total probability, which is, again, this piece here. And I really hate writing it this way. I think it's dumb, but whatever. And then plus, well, either A and B can happen, or A and not B can happen. So the probability of B complement times probability of A given complement. So that's probably what they're looking for with Bayes' formula. Again, I would definitely think about the diagram, right? If I know this, well, I'm thinking, all right, B or not happens. So there's B complement. And then after B or it doesn't happen, you can have A happening or A complement. Oops. I'm going to try and remember branches the same. So if I'm trying to find the probability of B given A, I'm saying, well, okay, I'm at all the ways A can happen, which are here and here, which is represented by this plus this, right? That's all the ways that A can happen. And then I'm finding the probability that B happens given that A is happening. Well, the way that B can happen is just, well, A's already happened. It's got to be, you know, this route there. So hopefully that kind of helps with the tree diagram. Yeah, I can definitely talk about Z-score. So hopefully, so the intention of the quiz was not to be super challenging. The intention was to first kind of explain it and then to help you, to kind of guide you through some problems. And so I should say first and foremost, there are different Z tables out there. And I know, I believe Whitener sent you guys one, but I don't remember what it looked like. So I'm going to go back to my usual example of IQ scores just because it's easy. So let's say we have a population where the mean IQ score is 100 and the standard deviation is 15. It's a pretty standard example. And we want to know a couple things. So first of all, what's the Z-score for the following IQs. Let's say we had an IQ of, I'm going to make up some numbers, so 130, negative 85, and let's actually do some harder ones. Let's say 110 and 95. Okay, so when someone says the word z-score, the thing you should hear is how many standard deviations away from the mean am I? So this one is actually really, really easy to answer. It's 2 standard deviations away from the mean, specifically 2 above. So without doing any work, we're going to do the work. But without doing the work, I know that the z-score here is positive 2. I don't know why I wrote negative 85 here, because I was thinking the z-score would be negative. There's no negative IQs. If you had an IQ of 85, you'd be exactly 1 standard deviation below the mean. So your z-score would be negative 1. And here's how you actually calculate it. So the z-score for any particular value x is your value x minus the population mean divided by the population standard deviation. That's how you calculate the z-score, aka the number of standard deviations. So here, the z-score would be given by 130 minus 100 divided by 15, which is exactly 30 over 15, which is 2. Here, the z-score would be 85 minus 100 over 15, which would be negative 15 over 15, which is negative 1. Here, it's a little more complicated. It's 110 minus 100 over 15, which is 10 over 15, which is 2/3, or 0.666 forever. And then here, 95 minus 100 over 15 would be negative 5 over 15, which is negative 1/3, which is negative 0.33 forever. So those would be the z-scores for those values. A positive z-score means you're some number of standard deviations above the mean. A negative z-score means you're that many standard deviations below the mean. Now, the question we often like to follow up with is, for each of these IQ scores, what percent of the population has a lower IQ score than that? Or if I have an IQ of this number, how many people am I, quote unquote, smarter than? I'll have smart's the wrong word. How many people do I have a higher IQ score than is really the question we're asking here. Well, for these first two, it's actually easy. We can use the empirical rule and say, well, okay, if I have a z-score of exactly 2, it means, I am right here at the mean plus 2 standard deviations. Now I know that if I'm 2 standard deviations on either side, I have 95% of the data. Right, so there's 95% of the data. There's 2.5%. There's another 2.5%. So I have a score that is bigger than 95% plus 2.5%, which is 97.5%. So this IQ score of 130 means that I have an IQ of 130 is higher than 97.5% of the population. Now, the thing is, you could also actually look this up in a table. And so I should have had a table ready to go here. Do I? I might. How much time we got? We got a few minutes. No, I don't see a z-score. Let's see. Okay, so you can look up a z-table. And I will say some z-tables, not every z-table is set up the same sort of way. Let me grab one real quickly here. I don't like the negative ones. Sure, I'll take this one. All right, let me share my screen, and of course. Okay, I don't want, close that little window there. Sorry, I just grabbed one from the internet. So here's a z-table, and here's what the z-table shows you. At least this z-table. For this z-table, any particular z value shows you how much area is less than that. So if my z value is 2, this is showing me that, let's see if I go over to 2. So, okay, so here's 2.00. I feel like that's not the right value. the area under the curve is 0.9773. Not quite the same as 0.975 because this is an approximation, right? The empirical rule is kind of a loose interpretation. So really, for a z-score of 2, we'd be greater than 97.73% of the population. Now here's an excellent question. This z-table doesn't have negative values. So if my z-score is -1, what do I do? Well, the z-table is symmetric. So I can say, well, I know a z-score of +1 has, in fact, can you guys see all right? So a z-score of +1 has 84% of the data less than it. So a z-score of -1 would have the kind of complement thing going on. A z-score of -1, right, would have exactly 84% of the data above it, meaning 16% of the data would be below it. So if your z-table doesn't have the positives and the negatives, you can always flip things around so that you can figure it out. It's kind of a pain in the butt, but it is what it is. So we could have used the empirical rule for those two. For the next two values, 0.66666 and -0.33333, we can't actually have to deal with the z-table. So looking at the z-table, here's what I've got. I was hoping I could highlight. So I'm looking at first this column, I guess. So look for 0.6, and then I go over to, I guess I should probably go to 0.67 because that's closer to what I actually have, 0.66666. So looking there, the value is 0.7486, meaning that for this IQ score of 110, we're greater than, sorry, what to say there, 0.7486 or 74.86% of the population. And in a similar way, if we're looking for -0.333, well, I know that for +0.33, looking at this here, +0.33 has 62.93% of the data. So I could say, well, okay. Sorry, I know my picture's getting a little out of hand here. So if my z-score was +0.33, I know that the area here is, I think I said 62 point something percent. 62.93%. So if my z-score was actually -0.33, I know that 62.93% is above it. And the complement, which is 37.07%, is below it. So that's how we could answer that sort of question. And then the other type of question I asked, which was something like, let me go back for a second. Let me stop sharing my screen for 1 minute. Eraser, what time is it? We got a minute, okay. So there's usually, in my mind, two types of questions with these scores. Like if you have some sort of score, what percent of the population are you above? And the other kind of question is, if you know you're above some percent of the population, what was your actual IQ score to begin with? So let's say we knew that let's say we were in, sorry, my brain is like trying to kill this. Let's say we were within the 60th percentile. Meaning whatever IQ score we scored was above 60% of the population. What was our IQ score? Well, to find that, we need to know what the z-score was. So looking back at the table, let me share my screen one more time. So I'm going to look, so now I'm looking in the table for 60%. So let's see, I'm looking at the 0.2 here, 0.2. So I see right here between 0.25 and 0.26, that's the score I need, right? So it's 0.2 for the first decimal, and then 5 or 6 for the second decimal. Now, since I want to be actually bigger than 60% of the population, I can't pick the number right here, the 0.5987, right? That's not quite bigger than 60%. It's bigger than 59.87%, which is not quite 60. So I have to round up to the next one. So my z-score is 2.6, sorry, 0.26, not 2.6. So to be bigger than 60% of the population, I have to be about a quarter of a standard deviation above the mean. So then I'm going to take that z-score, and remember that the z-score is equal to my score minus the mean divided by the standard deviation. And I'm just going to plug things in. 0.26 equals my score minus the mean over the standard deviation. And then I'm going to solve for x. So multiply this by 15, add 100, and that'll be my score, which is going to be, see, 15 times 0.26. That's 3.9 plus 100. So 103.9, which I'd probably round up to 104. So an IQ of 104 is going to be a higher IQ score than 60% of the population. So hopefully those examples kind of help you guys, answer those quiz questions. Again, they're not meant to be super hard. If you have questions, don't hesitate to ask me. And I guess we're out of time, so I should stop talking. I'll see some of you on Thursday, but obviously not everyone has to come. Also, I do have office hours today from 2:30 to 3:30, right? It's the later ones, yeah, 2:30 to 3:30. So if you want to come to the office hours, please feel free. The link should be on Canvas in either an announcement or a module or something. It's somewhere in Canvas. Please feel free to come. All right, on the meeting. Bye.